Hello everyone. We are going to discuss on the different types of LED. First of all, let us see what is LED. LED or light emitting diode is a two-LED semiconductor light source. It is a PN junction diode which emits light when activated. It works based on the principle of electroluminescence. That is, when a suitable voltage is applied to the LEDs, electrons are able to recombine with electron holes within the device, releasing energy in the form of photons, and the color of the light is determined by the energy band diagram of a semiconductor. Now let us see the energy band diagram of a semiconductor. When the PN junction is forward biased, the electrons in the N-type material which have been elevated to the conduction band and which have diffused across the junction find themselves at a higher energy than the holes in the P-type material. They readily combine with those holes, making possible a continuous forward current through the junction. The forward current in a PN junction, when it is forward biased, involves electrons from the N-type material moving leftward across the junction and combining with holes in the P-type material. Electrons can then proceed further leftward by jumping from hole to hole, so the holes can be said to be moving to the right in this process. Next, we will see some of the desirable characteristics of LED. It must have appropriate bandgap energy. The material must be suitable for both N-type and P-type semiconductors. The radiation pattern of the material must be transparent to the emitted wavelength. The relation between the wavelength of the emitted light from the LED and the bandgap energy of the material is E equal to hc by wavelength, where h is the Planck's constant and c is the velocity of light. Now let us see the difference between regular diode and LED. In regular diode, recombination is non-radiative, whereas in LED, recombination is radiative. Regular diode does not emit light, whereas LED emits light. Normal diodes are silicon or germanium with voltage drops close to 0.6 volt. LEDs have gallium arsenide or other semiconductor whose bandgap energy is higher, giving a higher voltage drop. Normal diodes output is lesser than LED. LED's output has more energy than normal diodes because there is more energy carried by light besides thermal dissipation. There are many types of LED. These are some of the types shown. LEDs are produced in a variety of shapes and sizes. The color of the plastic lens is often the same as the actual color of light emitted, but not always. For instance, purple plastic is often used for infrared LEDs, and most blue devices have colorless housings. Modern high-power LEDs, such as those used for lighting and backlighting, are generally found in surface mount technology packages. The main types of LEDs are miniature, mid-range, and high power. First is the miniature. Miniature LEDs are mostly single-die LEDs used as indicators, and they come in various sizes from 2 mm to 8 mm through hole and surface mount packages. They usually do not use a separate heat sink. Typical current ratings ranges from around 1 mA to above 20 mA. The small size sets a natural upper boundary on power consumption due to heat caused by high current density and need for a heat sink. Common package shapes include round with a domed or flat top, rectangular with a flat top, and triangular or square with a flat top. The encapsulation may also be clear or tinted to improve contrast and viewing angle. Figure 1 shows the photo of miniature surface mount LEDs in most common sizes. They can be much smaller than a traditional 5 mm lamp type LED which is shown on the upper left corner. Figure 2 shows a very small red, green and blue surface mount miniature LED package with gold wire bonding details. Next is the mid-range. Medium power LEDs are often through hole-mounted and mostly utilized when an output of just tens of lumens are needed. They sometimes have the diode mounted to 4 LEDs for better heat conduction and carry an integrated lens. An example of this is the Superflux package from Philips Lumileds. These LEDs are most commonly used in light panels, emergency lighting and automotive tail lights. Due to larger amount of metal in the LED, they are able to handle higher currents, that is around 100 milliampere. Next is high power. High power LEDs are high output LEDs that can be driven at currents from hundreds of milliampere to more than an ampere, compared with the tens of milliampere for other LEDs. Some can emit over 1,000 lumens. LED power densities up to 300 watt per centimeter square have been achieved. Since overheating is destructive, the high power LEDs must be mounted on a heat sink to allow for heat dissipation. If the heat from high power LED is not removed, the device will fail in seconds. One high power LED can often replace an incandescent bulb in a flashlight or be set in an array to form a powerful LED lamp. This figure shows the high power light emitting diodes attached to an LED star base.
Next we will see the types of LED based on location of transparent window. First is SLED, that is surface emitting LED. This type of LED is also known as Burus LED in the honor of C.A. Burus, its developer. In surface emitting LEDs, the size of the primary active region is limited to a small circular area of 20 micrometer to 50 micrometer in diameter. The active region is the portion of the LED where photons are emitted. The primary active region is below the surface of the semiconductor substrate perpendicular to the axis of the fiber. This diagram shows the structure of a SLED. A well is etched into the substrate to allow direct coupling of the emitted light to the optical fiber. The etched well allows the optical fiber to come into close contact with the emitting surface. In addition, the epoxy resin that binds the optical fiber to the SLED reduces the refractive index mismatch, increasing coupling efficiency. Next is edge emitting LED. The demand for optical sources for longer distance, higher bandwidth systems operating at longer wavelength led to the development of eLED. The primary active region of eLED is a narrow strip which lies below the surface of the semiconductor substrate. The semiconductor substrate is cut or polished so that the strip runs between the front and the back of the device. The polished or cut surfaces at each end of the strip are called facets. This is the structure of eLED. In an eLED, the rear facet is highly reflective and the front facet is anti-reflection coated. The rear facet reflects the light propagating towards the rear end, facing back towards the front facet. By coating the front facet with the anti-reflection material, the front facet reduces optical feedback and allows light emission. eLEDs emit light only through the front facet. There are two types of structures of LED, homostructure LED and heterostructure LED. In homostructure LED, The N-type and the P-type of the semiconductor are made from the same material. Light produced by the electron-hole recombination in the active region radiates in all directions, but only a transparent window on the upper surface or at the edge allows light to escape from the structure. All other directions are blocked by the semiconductor packaging. As a result, most of the light generated within the device is lost. Next is the heterostructure LED. Heterostructure LEDs are made from two or more different types of semiconductor material, each having different band gap energy. The two basic principles involved are carrier confinement and optical confinement. Confinement of electron-hole recombination within a highly restricted active region is called carrier confinement, and the conduction of radiated light in one direction is called optical confinement. This is the diagram of the type of heterostructure LED. Carrier confinement is achieved by placing a semiconductor having lower band gap in between two layers of another semiconductor material having higher band gap energy. Electrons injected from N-type aluminum gallium arsenide confront an energy barrier at a junction where gallium arsenide and P-type aluminum gallium arsenide meet and are reflected back into the active region. The same mechanism works for holes also. Optical confinement is achieved because the refractive index of gallium arsenide having refractive index of 3.66 is higher than the refractive index of the surrounding layer, that is aluminum gallium arsenide of refractive index 3.2. Thus the active region works like a waveguide, similar to an optical fiber trapping light within the core. A special type of LED is superluminescent LED. It is an edge-emitting semiconductor light source based on superluminescence. It combines the high power and brightness of laser diodes with the low coherence of conventional light-emitting diodes. Its emission band is 5 to 100 nanometer wide. This is the diagram of a facet feedback and wavelength resonances in the optical emission spectrum of a multimode Fabry-Perot laser and powered spectral density of a superluminescent light-emitting diode. A superluminescent light-emitting diode is similar to a laser diode based on an electrically driven PN junction that, when biased in forward direction, becomes optically active and generates amplified spontaneous emission over a wide range of wavelengths. The peak wavelength and the intensity of the SLED depend on the active material composition and on the injection current level. SLEDs are designed to have high single pass amplification for the spontaneous emission generated along the waveguide, but unlike laser diodes, insufficient feedback to achieve lasing action. This is obtained very successfully through the joint action of a tilted waveguide and anti-reflection coated facets. When an electrical forward voltage is applied, an injection current across the active region of the SLED is generated. Like most semiconductor devices, a SLED consists of a positive section and a negative section. Electrical current will flow from the P section to the N section and across the active region that is sandwiched in between the P and N section. During this process, light is generated through the spontaneous and random recombination of positive and negative electrical carriers and then amplified when traveling along the waveguide of a SLED. The PN junction of the semiconductor material of a SLED is designed in such a way that electrons and holes feature a multitude of possible states with different energies. Therefore, the recombination of electron and holes generates light with a broad range of optical frequencies, that is broadband light. Now let us see some of the application of LED. First is flashing. Flashing is used as attention-seeking indicators without requiring external electronics. Flashing LEDs resemble standard LEDs, but they contain an integrated multivibrator circuit that causes the LED to flash with a typical period of 1 second. In diffused LEDs, this is visible as a small black dot. Most flashing LEDs emit light of one color, but more sophisticated device can flash between multiple colors and even fade through a color sequence using RGB color mixing. Next is bicolor LED. Two different LED emitters in one case. There are two types of this. One type consists of two dies connected to the same two lids anti-parallel to each other. Current flow in one direction emits one color and current in the opposite direction emits the other color. The other type consists of two dies with separate leads for both dies and another lead for common anode or cathode, so that they can be controlled independently. Next is tricolor. Three different LEDs emitters in one case. Each emitter is connected to a separate lead so that they can be controlled independently. A 4-lead arrangement is typical with one common lead and an additional lead for each color. Next is RGB. Tricolor LEDs with green, red and blue emitters in general using a 4-wire connection with one common lead, anode or cathode. These LEDs can have either common positive or common negative leads. Others, however, have only two leads and have a built-in tiny electronic control unit. Next is alphanumeric, available in 7-segment, starburst and dot matrix format. 7-segment displays handle all numbers and a limited set of letters. Starburst displays can display all letters. Dot matrix displays typically use 5 by 7 pixel per character. 7-segment LED displays were in widespread use in the 1970s and the 1980s, but rising use of liquid crystal displays with their lower power needs and greater display flexibility has reduced the popularity of numeric and alphanumeric LED displays. Thank you very much for listening.